Yeah, let's wait a little bit because we only have 22 people right now. So wait maybe 2 to 3 minutes before we get started. In the meantime, if any question, please let me know. Maybe let's get started with some announcement first. I guess this tomorrow we'll have a deadline for homework 2. Um, Homework 3 has been uploaded. Um, so if you have time, you can take a look. There will be deadline will be 13th of November, the same time where the peer review also there. Okay. Some of you may notice that send me the email saying for the peer review, your PDF document is not there because due to the fact that you submit your document in multiple attempts. I only download the last attempt. So if you happen to submit a different attempt, then I would unable to retrieve it. So let me know. I add it back if you submit in several submission, but shouldn't be a big issue. Um, and the exam will be on the November 26th at night, 7:30 to 9:30 p.m. Hong Kong time. That is to make that even if you're in our time zone, that is still a feasible option for you to do it. And if you happen to miss it with legitimate reason, then let me know in advance. Otherwise, you have to take the one. Is there? Is it tomorrow? 13th of November. Is it tomorrow? Let me check. Is it tomorrow? Maybe I just. I think it's 30th. No, 2002. Is it? Oh yeah. I think I just didn't put the 13. Yeah, sorry. Yep. You will be looking at all others' work, and then you will be evaluating that. You just need to say it's above average, and below average. That is what you need to write down. That would be the zip file. So to demonstrate, right? I think. Let me show you the screen, I guess. Announcement. I think in the peer review, let me show you. In the peer review here, the oh sorry, not assignment 2, assignment 1 is a peer review on that. And just fill in the form here, just say above and below, and that's it. Yeah. So no need to have any further work, just below above, that's it. And the I will give you more information about the projects, and also the exam will be open book, right? It will be given there, and the project will be also given soon. I will upload that soon about the instruction to do it. But you were doing the last 2 classes will be doing presentation. So I had to figure out how to do the when the people different time zone. So possibly if you're a different time zone, then I allow you to record. Otherwise, you'll be doing a real time presentation. That's pretty much of that. Yeah, that's pretty much of that. Any question? Any question before we proceed? If no, then no question. Okay, that's good. So just a gentle reminder that the remaining class of this course will be online due to the policy of the business school. So and also your choice too, because majority of the classmates chosen online, so will remain online. You can open it because the RAR file. Is it that you need, if you are in the Mac, you need to use this one. You need to check how to do it in Mac. Yeah. Yeah, Mac, you need to use some way to open it. Okay. The reason I use RAR because the school use RAR as a default way to zip file. So maybe next time I should use WinZip, whatever. I mean, that would be much easier. But anyway, any question besides that? If no, then we will be having a class. Just today we'll finish the 1 sample and then start with the 2 sample hypothesis testing. But the fact that we are just on time, so we will be combining the 2 quizzes together. So we will not have quiz next. We will not have quiz next class, but instead we'll wait until this whole hypothesis testing chapter to end, and then we will have the quiz for the both topics. Due to the fact that we are a little bit behind schedule, slightly, so we'll just save some time. Okay. So if there's no further question, let us go to hypothesis testing. So let us review what we have learned so far, and then we will wrap up the one sample test. So hypothesis testing again is we've talked about 1 sample. We have 1 sample from 1 population. It's a random sample, and based on this random sample, we're interested in mainly for a case where is the mean lies. Okay, usually you want to see whether the mean is equal to a certain number or not, right? And later you will see this very relevant when you do regression, right? Later you will see, but this is something we care is about the null hypothesis is usually mean equal to certain value. Okay, that will be basically most of it, except where last test we're doing use, but otherwise it would be basically mu equal to a certain number or not, or the population proportion equal to a certain number. And the alternative have two types. Either you have one tail or two tail, right? Whether you have one tail or two tail or one side, two side depend on what usually was a consequence of that, right? Or what is the prior knowledge on those, right? So that would be something we would care. And we have alpha and beta is a type 1 type 2 error. And rule of thumb, the alpha is either 0.1, 0.05, or 0.001. So that is the rule of thumb. And there are two ways to do this procedure, right? Regardless of the way you will state the null and alternative hypothesis, you construct the test statistics, and then you compare your test statistic with the critical value, or calculate the p-value based on the test statistics. Okay, and whether you know the sigma will give you different two tests, either Z or T, and very often you do T because it's not easy to say you know it, but somehow you know it, then it's easy. But you don't know it, then you rely on T, and most of the time you rely on T. Okay, except when you talk about proportion, sample proportion, you can later you will see you will have P. You can have the Z test. You will see very soon. And it depends on whether you reject on the right or the left. On the right, then the rejection region is on the right, all right? Because when you say mu equals a certain number, and you want to try to see is the alternative is more than that. If it is far beyond that, then you reject, right? So just a very gentle reminder of how we do this kind of question. Actually, we'll be doing this all the time, right? It's just say X bar, right, should be somewhere A according to the null hypothesis, right? And we are rejecting, saying that it's too big, right? So it is far here, then you reject, right? And how far is far, right? We are saying that the threshold we are using is this area is less than alpha, make it less than alpha, then it's far away enough, right? So basically what we're doing is trying to look at the Z space instead, right? And look at the Z and normalize, this becomes 0. And if you look at the alpha fraction, right? Just look at the Z alpha, okay? You want to really check your sample, what you figure out, which is here or here, right? Depend on the sample you figure out, right? If here, right, then you don't reject. So if here you reject, if here, then you don't reject, right? Because this is the rejection region. So you will be the same, this example, I mean, when you have the other way around, less than, then you reject on the left. So it's far left, then you reject, right? I'm not going to repeat. It's a mirror image of what we have found. So the difficult part is the two-sided test. In that case, you would put, you calculate the p-value will be 2 times. Okay, so that is the most tricky part, is 2 times of this value. Okay, if less than, then we reject. Okay. Any question? Any question before? Okay, if no, then we will continue with the T. So T will be used when we don't know the population variance, which is fitting the most cases. We don't have a good idea what the sigma is. So in that case, we would be saying that mu is A and mu in the right tail test, right? So we just, again, the same idea here, but from X bar, but now we are not going to the Z, then you go to T. Okay, the same idea, everything is same. You look at this area, alpha area. If what you figure out is within this alpha area, then you reject, otherwise you don't. Okay. So the right tail is here. Okay. Now let's go to the left tail. So this is what we have covered so far from last class. But is there any question? If everything okay, then can you type okay? Or you have any question? Very good indeed. So let's repeat what we are doing here. Just you will see we are repeating all the time because this is the technique that we are using. So from a random sample, right, the sample mean will follow a normal distribution, right? And this, assume this is true, A is here, right? The sample mean is, the mean of the sample mean is the population mean, right? And we know that this can be converted to T, right? Just if you minus the mu and over S over root N, right? We have the distribution with mean 0. Okay. And now we are rejecting on the right. It's too far right there. We put the alpha, right? Then you would reject, right? So we convert to this here, right? This will be the alpha. This, again, alpha here. What's this number? Is T, N minus 1, right? Alpha, negative, right? Because the left-hand side. Okay. So if to calculate the T, right, is within this region, then reject, otherwise you don't. Okay, so that is the basic idea behind all this. Okay, let's go to the example. Okay, and now we have to repeat. Now we have sample size of 16, sample mean of 3, and standard deviation of S equal to 2. Okay, and now we have now is 4. The alternative is less than 4. Okay, so we write here, we have X bar, right? The mean is 4 under the null. Okay, this is drawn under the null hypothesis. Okay, and this is 4, right? And the thing is, we figure out this is 3. Okay, and the question is it small enough to say rejection, right? So just the idea is either is this area below 3, is it less than 5%? We use 5% as a standard way to do it. Okay, is it less than 5%? Okay, if less than 5%, then yeah, then we can reject, right? Otherwise, we would be not rejecting. Okay. So to do it, right, one of the ways we have to know what is this distribution of this, right? And it's not easy to understand this one, but we do know that this can be converted into T, which we know how to calculate, right? It would be T n minus 1. In this case, it's T to the 15, okay? So with a bell shape because it's T, okay? This is 0. And how do you convert 3? 3 is what? Okay, how do you convert 3? You go to what value, right? Conversion comes from the formula. How do you convert, right? It's X bar minus mu over S over root N, right? And this mu is 4 here, right? S is 2, n is 16, right? So that's this equation. The numerator is -1, the denominator is 1/2, so that's give you -2. And look at the t table, okay? There are two ways to do it. One way, the second. Let me do the second way first, okay? What is 3 here? Okay, 3 is -2, okay? So the thing is we want to figure out what is this area, right? And very directly, this is the standard inverse function, right? So just like how to figure that out is just t dot inward, you put -2, sorry, it's not inverse, it's standard this, sorry. This 2, and degree of freedom is 15, and this is true, okay? And this Excel function will give you this number, and this number is less than 5%, right? Then we'll reject. Is that okay for this one? Okay, no question. So let's do the alternative way, right? Instead of look at this, we do the other way around. So what it's doing is, let's check what is exactly 5%. Okay, what is this value, right? That means this value, what is here? 5%. Okay, and this value is what? This value is nothing but T15, right? Negative 0.05. Okay, and this value, how do you find this one? Okay, this comes from T inward is either you look at the 5% or you go the other way around, right? This number, you can put 0.05, 15, okay? We'll give you the negative because it's here, right? So give you negative. Then this should give you the answer of this from Excel, okay? So since this number is less extreme than this -2, so we will reject because this is 5% and it's even further away, then you reject. And someone asked me in the chat whether we need to do both, okay? The answer is no, you just do one of them, okay? Just do one of them. Someone asked me, is it writing is less than, right? You have to, you need to follow similar to what I write here. You calculate this, less than this, and I mean, of course, you say we reject at 5%. That is something standard. I think you can check the textbook, what is appropriate, but I think that what I write here is the standard way to do it. Of course, you can write how you get this number, right? You can to be more more explicit, you can write using this is there, but otherwise shouldn't be an issue for assignment or exam. Maybe exam you should write what is the Excel function to figure that out. I guess that would be, maybe I will explicitly say, I mean, if you use, that would be the case. Any question? As long as you write everything explicitly and it's clearly that you calculate the result, then I think I don't see there's a big issue. But the thing is, you make it clear that how you arrive the answer. But is that okay? Up to now, any further question? If there's no further question, then I will continue. So yes, I think it's online, so that's why I guess you can use Excel because I cannot really not allow you. I mean, I can't see it, so it's very difficult to stop. Doesn't mean that if this class is going to be not this semester, in the next semester, if I ever teach this class, then probably you will not, but no. We can use Excel, but you Excel, you say what is the function you're using. Yeah. You can just tell, okay, according to this function, you input and that's it. I think it will be very clear what you will be writing down there, but you write a full step to arrive your answer. Is that okay? Is that clear, check me? Just make sure that your step is clear, and that's what I want to ask. I mean, you don't want to give me the impression that you are just doing this by luck, right? Otherwise, that would be the main criteria we are using to see whether you get the solution. Yeah? And also, if you skip too many steps, then if you get it wrong, then there will no intermediate step marks will be given, right? So if you skip too many steps, then it will be easy. Okay. So now we're two-sided test. Okay. So same idea here is X bar. Okay. It's a normally distributed. Sorry, not normally, but kind of this shape. Okay. A normal distribution, right? This right will follow a normal distribution with mean mu sigma square over n, right? This is by central limit theorem, right? And then this will be the A here, right? But we don't know this, we cannot convert to Z, right? We'll convert to T here, right? 0, right? N minus 1. And now the thing is, we say is not equal to, right? So there will be rejection on both sides. And we put alpha divided equally on two sides because don't know, then it's fair to use both sides, right? Alpha 2, right? Then you expect the boundary or the critical value will be Tn minus 1 alpha 2, right? This will be negative Tn minus 1 alpha 2. Okay, so I hope that should be not a big issue. Okay, so given that we have done so many already, so let's see the example. Okay, so will be very similar example again. We have the X bar, right, according to the null hypothesis, right? Have the mean mu equal to 4, right? Sigma we don't know. I mean, that's why we don't know how this is shaped. But we know the sample standard deviation is S, is this, N is 16, and N is 3, then we can say this is T distribution, right, with degree of freedom 15. Okay. And this is 0 here. Okay. And you want to look at these two areas. Okay. what you find out, this is the sample is free. Okay, so you want to see whether this area is it less than 5%. Okay, so how you convert 3 here? Okay, 3 you will subtract the mean over the standard error, right, which is 2 over root 16, give you -2. Okay, so here you go down, here is -2 here. So the question is the 2 way to do it again, 1 or 2. Let's do 2 first. 2 is more direct, right? So you want to check is the area 2, how big is it? Sorry, I think it's not 5% here because we're two-sided. So we need to check where this area is 2.5%. Okay, because you don't know where, before you do the sample, you don't know where it is, so you put both sides 2.5%. Okay, so you are checking whether it's less than 2.5% on one side or the other. Okay, so there's only tricky part here. Okay, so how do you find this area less than -2, right? That is very standard. How you find that? You will be T distribution -2, degree of freedom is 15, right? True. Okay, this will be the area. And because of you want to compare with 2.5% or you compare with the P, so that's why you compare directly, right? Either you compare this with 2.5 or you compare with the P, right? Because the rate, either you compare P with alpha over 2, right? Compare this value, we call P, or you calculate the 2P, compare the alpha. They're the same thing, okay? Or this probability. And you define this is the P, right? So one way or the other, you compare this area and turn out this is more than that, then you can't reject. Okay, now you can see we failed to reject. Alternatively, you can calculate both sides 2.5%, right? So you want to see whether this is 2.5% and this 2.5%, okay? What is this number, right? This is T15.025. Okay, how to find this number? So this is coming from this formula in the Excel, right? T inward. If you calculate this positive, it's 0.975 and then 15. Okay. If you put this, it will give you a -1, right? If you put this guy, we will give you this number. Okay. And you can see the -2, right? You see it, right? So it's -2 is not inside the rejection region. So you fail. Oh, sorry, I should be 2.5. Sorry for that, it should be 2.5. So you would fail to reject. Okay. Any question? Any question before we end the section with the proportion? Any question? Yeah, purple pie is 2.5%, yes. Any more question? Because 5%, so both sides 2.5. Okay, if there are no further question, then we will be looking at the next one. Proportion. So I just add one more slide just to recall what we have learned. Okay, just to let you know, we will always use Z, so don't need to use T for proportion. The reason why is under the null, suppose the null is pi, we already know the sample variance. The variance of sample proportion will be this one, right? Because we learned this, right? P will be normal pi, 1 minus pi over n, right? When n pi bigger than 5 and n 1 minus pi bigger than 5. So it shouldn't be an issue here. And most of the time it's satisfied anyway. So that's why you can always use that. Now, that is the same thing. This is remember this is also sample mean, right? Some proportion, but the data is binary data, right? So we check whether the proportion equal to a certain number, right? And we know this is a normal. So everything is the same, okay? We will do two-sided test, but the one-sided one is the same, okay? Although we do two-side only, but one side we follow the same procedure. We just do one and two side again to show you how we do it, okay? So let's do it again. The same question here is we have a sample proportion, right? With the sample mean under the null hypothesis. This is 0.4, okay? We already know if this is true, we already know how this is the variance of this, right? Will be the variance of P will be equal to 0.4 times 0.6 over 50. Okay, so this is what we have learned. Okay, so the question is what you figure out is the sample proportion is 0.5. So the question is now is here. Okay, and we want to see this is it far away because it's not different, right? So we want to check. Now it's on the right hand side, but we want to check this is it less than 2.5% because you don't know where to reject. But if you do two-sided, right, then you assign half of that, right? So it's 2.5%. It's less than 2.5 or more than 2.5. Okay. So what you're going to do is to look at this, right? You convert it to the Z, right? Not T, but Z because we know where the distribution, right? So we just convert to Z, you know, it's normal, right? So this becomes 0, right? And we want to convert this 0.5, how we convert, right? You know this number, you know this number, you know this number, that's normal. How you convert this, subtract this over square root of this, right? So that's why 0.5 minus 0.4, okay, over the square root of this, right? It's 1.44, okay? So it's 1.44, okay? So we want to check what's this area, okay? We know it's normal, so that should not be a difficult task to do, right? How do you arrive this answer, right? Will be calculate this area first, will be the norm S, 1 minus, because the Excel calculate left hand side, so 1 minus distribution, right? 1.44 and then true. Okay, so this gives you the area. You can compare them with 2.5 or you multiply them, compare with 5%. Okay, and turn out that is 10% something, so you cannot reject. Is that okay? Because the Excel, someone asked me why I did my minus, but the Excel always gives you the left hand because the norm as this is what? Is the probability that Z is less than Z. Okay, probability less, this left hand tail is the tail, is the area on the left. But we want the thing on the right. Is that okay? Now, this is the method 2, right? We're done. So let's do method 1. Maybe use other color to be more clean. So method 1. So method 1 will be looking at what is 5% area. Okay. So we try to look at if this area is 2.5%, what is this area? Is it less than that or more than that, right? If more than that, then you would reject, right? So we want is Z alpha over 2, right? How to find C alpha 2? This value, right? C alpha 2 will be the norm S inward, right? Again, we have the left hand side, right? So we would inward is 97.5. Okay, so this should give you this answer, and this is beyond that, then you would say you would fail to reject because the red one is not within the blue one, the rejection region. Is that okay? No, because we're looking at this area. We're not talking about the 1 minus. No need to 1 minus already, because this is asking you. Okay, this what it's doing is reverse, right? This is what is the Z give you this. This is reverse case. Is if this is 9.975, what is this Z? This is Z number, right? So I guess that's pretty much of it. Any question? Any question? So let us very briefly review what we have done because we're done with the one sample. So this is we finished one topic already. So after the break, we talk about the 2 sample. So let's very briefly review what we've learned. So it's a 1 sample. So maybe I use okay, so let's review. We have hypothesis testing. Okay. What we have is 1 sample. And this is 2 sample, which we will cover after the break. Okay. And for 1 sample, we have 2 things to look at. One is standard numerical data. Okay. One is binary data. Okay. And for binary data, the sample, we care about proportion, right? And this is we care about the sample mean, the mean, right? And we want to see whether the sample mean or sample variance sample mean equal to what or sample proportion equal to what, right? And if we know the variance, if I know it, then I will use a Z test, right? If I have the variance, I don't know it, then I use t-test, right? The proportion I always use c-test, okay? And whether you use one-sided or both-sided depend really on the knowledge, the outside statistics, right? Whether you want to say from the problem, you see whether violation of this with a consequence and what you want to do, and that would be the key. Okay, so after the break, we'll talk about this. So let's have a break of 15 minutes. We'll resume at 5 5:30. guess we should resume. Any question before we resume? Any question? If you know, we will start with 2 samples. Okay. So before we start, let me talk about what we're going to cover in this set of slides. I add one slide here just to give you a overview what we're doing, but just nothing added, but just a more structure. Okay. So what we have is one sample test, right? And now we have 2 sample. And what 2 sample here is, we often even though we have data here, right, the population here, we may collect some variable interest we care, maybe income or GDP or GPA or whatever we care, right? And besides this number, usually we also obtain the characteristic of the observation, right? Maybe gender, maybe education, maybe many things. So we are interested in whether this grouping would make a difference, right? Whether, say, for example, in gender study, which is something become increasingly common these days, gender studies, right? And you want to see where gender have any impact, right? Suppose you have a male or female, right? And usually male or female are independent, right? Because whether you are male or female is given by birth, right? So when you're born, you are born to be male or female most of the time, right? It's not something by choice. And in that case, then you can consider this an independent draw, right? And you want to see whether the male or female have impact on, say, your GPA, right? Whether the GPA of the male, right, is it the same or not of GPA of the female? Okay, this is a question, right? Not GPA, maybe spending, also spending. Maybe you want to look at, as an Apple company, you want to whether the people willing to spend on the iPhone, say, right? iPhone spending on the male or iPhone spending on the female. Okay, whether this is the case or not. Okay, or you want to see as an auditor, you want to see maybe a size A and size B, whether the mean of certain inventory is same between them. Okay, and we have 2 independent population, as we have said just here. Okay, and you want to check whether the mean are the same or not. Okay, and the underlying 2 things is whether we assume they have same variance or different variance. They will give us very different way to test the hypothesis. Okay, if they're the same, we have one way to do it. If they're not the same, we have that way to do it. Okay, so if the same, then we will have some way to estimate. If they're not the same, the other way. Of course, we assume the same, then we have more precise estimate. If we're not the same, then we have less precise calculation. Okay, that will be 2 different formula. Okay, probably we finish 2 in this class. The next 2 will be left in the next class, which we'll do the other way. The other thing which is not independent is actually is pair. Okay, what we observe is in the population. Okay, we have a single individual, maybe have 2 observations. Okay, so maybe it's before, it is after, which often used when we look at this is before, okay, and this after. And usually what common here, this is treatment, okay? Maybe drug, okay? Right now we have COVID-19, right? And try to test a drug or a vaccine, whether useful before and after, right? You want to see whether there's impact on those, right? And also you want to see maybe there's new law, new regulation, and see the regulation, whether they change it or not. Okay, so that's a very standard way. And you can see these two observations are related, right? They're talking about the same person, and that is before and after, right? So that would be it. And this is related to that, right? Another observation, okay? Before, we don't have any association with one observation and other, okay? There's no link between them, okay? Same for the GPA, right? They're two different people, and iPhone are different people, okay? But this one, we're exactly the paired observation. So the number of sample B and sample A will be the same, okay? The same. But in this case, the observation and sample size from the male may not be the same as female. Can be same, but there's no limit to say they're the same, okay? Because we have male and female can be very different, okay? And this what is the paired population means, or what we sometimes call match the sample if you use the textbook, match the sample, okay? And this is looking at the mean, okay? At the end, also look at the variance, okay? We want to check whether the independent population, we want to check whether, say, is it the male have the same variance or female have the same variance, okay? Well, the same or not. So the question is, okay? And of course, this can help us to talk about whether they have equal variance or not, right? This, if you do this or not, then it can help us to decide this case or not. But that is the thing that we care. Okay, so that's why all of these are very useful thing. And of course, if you do the project, which we will talk about more later, then you are welcome to do this 4 tests if you have the data. Okay, any question before we proceed? This is the overview of the rest of this class and also the next class. Okay, if there's no question, then we will proceed. Okay. So we'll start to have some weird looking formula. Okay. So the question now we have is we have, okay, just to remember 2 sample 1, sample 2. Okay. The sample 1, we have again mean mu1, right? We have the equivariance, okay, so it will be sigma over n, mu2, sigma over n, okay? So what is asking is the difference, right? Mu1 minus mu2, okay? And we learned that from the sampling distribution, remember from the normal distribution, right? The difference, mu1 minus mu2, right? We have a normal distribution, okay? With mu1, so the n1, n2, because they may not have same sample size, right? Mu1 and minus mu2, okay? And what is this? Because they're independent, actually we'll prove it. It will be sigma square over n1. So that's here. Plus sigma square over n2. Okay. So that will be, right, because the expected value is this guy and variance of this guy. We'll prove this variance, why this is true. We'll prove this variance of this is this, why ex of this is this. We'll prove it, but that will be the key, okay? And we know this follow a normal distribution, all right? Asking if they're the same, so it will be 0, okay? The variance following this one, okay? So we want to see, we have the data, we collect 2 samples. two sample mean, right? We want to see whether they're different or not, right? So again, the same idea, we use two-sided one. So look at this area, alpha over 2, alpha over 2, okay? And we want to see whether it's alpha over 2, right? We just try to get the data and see whether they're the same, okay? And we will proceed directly to t-text. We assume that we don't know sigma because, of course, we can say we know sigma what to do, but for simplicity, we skip that part, okay? Because you will easily see, because it's normal, we can easily check based on, if no sigma, basically things become trivial, right? Because you know sigma, then you'll be just x bar 1 minus x bar 2, right? Over the square root of sigma square over n1 plus over n2, okay? So the thing is, we don't know sigma, then we have to replace by the sample version. So what's this sample version, right? So if this, you know, then this is z, right? You don't know, then you have to replace by the sample version, okay? Then what's the sample version? Okay? So that is the main question that we are trying to answer, okay? And this turned out, this is a rather interesting funny thing. Once we play this, this will become a t, which will also prove it. So we'll prove these two part. This funny thing will be t, okay? But what is this part? Just to define it, we'll try to prove it. So this will be equal to this funny shape, okay? How to estimate the variance will be this funny, these two funny expression, okay? This is the average, weighted average of these two variance, right? This is a sample variance of the first sample, the sample variance of the second sample, and the weighting will be determined by the sample size, right? The larger the sample of the sample one, then you have more weight, right? Because the denominator are the same, right? The numerator is the sample size minus 1. If the sample size is larger, then we will tip towards this one, right? This is the weighted average of weight depend on how many sample you want, right? The larger the sample, the more important, right? So you should know that is the SP, right? Must be between S1 square and S2 square because it's weighted mean, okay? The weighting determined by the sample size. We'll prove it. And the critical value is this one because of the t distribution, right? And also we look at the two tail text. If one tail, then depend on the tail you're looking at, then will be minus 2 alpha, right? If one step is a one-sided text, depend positive or negative, depends on which side you look at, right? If right tail is positive, left tail is negative, okay? And similarly, you can have a convolutional interval estimator, okay? The difference can be estimated by the same technique we're using, right? With the t, and this is standard error, right? This margin, this is the SE, right? Okay, so let's see the example. I mean, there's a lot of formula here. Let's see how it works, and then we will explain why this formula works. Is that okay? Is that a question? If that's okay, then can you type okay? Because I think a lot of thing goes on here. Good. So you guys are much better than I. Standard error. Standard error is, so if standard error, the standard error is the square root of the variance of the mean, sample mean. Okay. All the time, actually, when we are talking about the denominator, actually the standard error here, but we don't use the term directly, but this is what we do, right? This is the standard deviation of this guy, right? That's So now let us go over this problem line by line, because I think that would be important. So we have two population have same population variance, okay? And with a one random sample with size 50, so N1 is 50, okay? And X1 bar is 40, and S1 is 4, so this is what is given here. And the other sample from other population, right? So N2 is 40, X2 is 42, and S2 is 3, okay? So we are looking at are they the same mean or different mean, right? Do note that this is coming from two different sample, two different population, okay? Two different population, right? This population 1, you draw from here. The population 2, you draw from there, okay? And you want to, this with mu1, this is mu2, right? You want to see whether mu1 and mu2 are the same, right? Just to recall, while you do that, this is maybe a bunch of men, there's a bunch of women, you want to see a difference, right? Or a bunch of people who live in Hong Kong, a bunch of people live in the New Kowloon, then you can see a difference, okay? And the formula here will be, just to recall, SP squared, right, with S1 squared plus S2 squared with the FH, okay? The weighting will be just N1 minus 1, right? N1 minus 1 and plus N2 minus 1, okay? This is the weighting is like this, okay? So that's why 50, 50, right? 50 here for N1, N2 for 40, right? So that's give you 12.89. So remember we said, right, S1 square is 16, S2 square is 9. So this pool must be in between the two, right? And you can see the sample size N1 is bigger, so it would tip towards 16 rather than 9. Okay, because I think 16 plus 9 divided by 2 will be 25 over 2 would be 12.5, right? So it would tip slightly towards S1, right? Because S1 sample 1 is bigger, okay? Bigger than the sample 2. So slightly more than the average, okay? You can see if N1 equal to N2, right? If N1 equal to N2, right? You can easily see SP square will be just half of S1 square plus half of S2 square. Okay, so this is something that you may see from this expression. Okay, and now we want to calculate. Now we have this pooled sample, right? Then we can calculate the t value, right? Just to recall the following, right? What we care is this guy, right? And we have claimed this is 0 under the null hypothesis. Okay, the difference would be 0, right? Because this is mu1 minus mu2. And the sample we get is mu1 minus mu2 is negative 2. So is what we have is here, negative 2. Okay, we are trying to see this guy. If two-sided test, we want to see if this is less than 2.5% here. Okay. Is that clear what we're doing? And what we are trying to do now is look at the t here, right? We convert it to here, right? And we want to see this 2, what? Oh, because why? Some ask me why this is 2. This is just x, the sample 1, 40 minus 42. Okay, this is what we can figure out is less than 2.5 or not. So we want to convert this to here. Okay, and how do you convert, right? Will be just this is the value, this is the mean, you just over the square root of the variance, right? The standard error, right? Which is, we figure out this is the variance of this, right? The variance of x bar 1 minus x bar 2, right? Will be, right, equal to this, right? And then we want to use the sample version, right? Will be this guy, right? The sample version. Okay, so we're using this to do this, then we can do T, right? So that's how you get this. This one, we have to figure out this here, right? So we just put that in, then we can divide by like that, then we'll be done. Okay, so let's see. So that is -2 comes from here. Okay, and this is, we just from last slide. Okay, this is N1, this is N2, right? Because this is formula, T will be x1 bar minus x2 bar, right? Over SP squared 1 over N1 plus 1 over N2. So this is the formula, right? And do note that this is have T distribution of N1 plus N2 minus 2. Why minus 2 we explain shortly, but that would be the formula we need. Is that okay? Up to here now, okay? And you put all this number, it's negative. Okay, so just go back to what we have here. 0, x1 bar minus x2 bar. Okay, this is -2. And you convert to T space. T N1 plus N2 is 90, binds to 88, right? Okay, you convert it to here, would be -2.625. Okay, so there are two ways to do it. Okay, one way is look at the p-value, right? Because again, this two-sided test, right? Look at 2.5%, okay? Or this value multiplied by 2, right? The p-value. So how do you figure out this value, right? Given you have this, T88, right? How to find this value will be T distribution, right? -2.625, true. Okay, we'll give you the, sorry, you have to put in the degree of freedom, I forgot. So T this 2.625, degree of freedom 68. So this will give you the answer of this area, but you need to multiply by 2. Okay, because you want to compare alpha. If you compare with alpha over 2, then you don't need to compare by 2. But by default, the p-value is over 2, then we'll have our mind easier, one way or the other. Okay, so this area is 0.01, so it's less than 5%. Is that okay for this step? Okay, is that no question? The other way around is look at what is the 5% area, right? Look at, so if this is 2.5%, what actually is this number, right? Which is T88.025, okay? So this area is 1.978. How do you find this? Again, let me repeat. This would be T, because you are, give you the probability, give you this is reverse, is T inverse, okay? And 0.025, and we have 80 degree, okay? This should give you -1.987, okay, with the answer. Okay, and you can note that it's here, right? Negative 1.97. So it's our test that is far bigger than this one, so we reject. Okay, so either there's a one-way or two-way. Both way will lead to rejection. You just need one. Okay, and how to do the interval estimate, right? They're different, so this will make sense. You take a difference, which is 2, okay, and plus minus this guy. This guy is coming from here, okay, and this guy go to here, right? So that is, as we have said, right, in the hypothesis testing and the confidence interval estimate will be closely related, right? You can see this, there's a critical value is here, and the denominator is here, right? The numerator is here. So everything is closely related to each other, right? So that's why I said it's very related in that sense. Any question? Oh, do you note that in your slide, I think there's a typo. So it is, this one is correct in here, but I think in your one is more than. Just make sure that you correct it, because it's obvious there's a mistake, but is it okay? Yeah, this is correct, but I'm not sure the one you have is, yeah, make sure that you correct accordingly. Okay, if there's no further question, then well, this is defined as p-value, so this is the standard thing. So I would recommend when you say p-value, you use 2 times when you have two-sided. I mean, I mean, you understand the logic, but that is the, people always compare p to alpha. There's no particular reason why that's the case, but we just try to follow this tradition, right? Because I mean, you either do one way or the other, but this is very standard, so I don't want to violate from that. Is that okay? If there are no further question, I try to prove this for you. Okay, the proof not be difficult, but this proof will be somewhat easy. Okay, and here is straightforward. Actually, we've shown it, right? Because x1 bar minus x2 bar, right? The expectation, right? It's just mu1 minus mu2, right? And the variance coming from the fact that they're independent, right? Independent sample. So independent, just add up, okay? And this is have the variance sigma square over n1. This is sigma square over n2. So that's why like this, okay? And do remember this is a normal, and this is also normal, okay? So the difference of normal would be a normal, okay? So that's why we have this function standard normal. Okay? I hope that's not an issue. We have discussed it already. So the more difficult part is this one. Okay? How do you prove this guy? Okay, how to prove this one? It shouldn't come as a surprise. Later you will see that actually the proof is also very easy. Okay? So sample 1, right? Observation will be given by this, right? Sample 2 observation by that, right? And they're independent, right? So that's why this property will also hold. This is coming from what we learned 2 chapters ago. We said xi minus x bar square over this, okay, is follow a chi-square n minus 1, right? And you just add, now the difference is just you add 1 here, add 1 here, right? And 1 here, right? So that's what it is. And the numerator, right? The numerator, sum of this, right, is equal to this guy. This should not come surprise to you because S1 square. So the summation square divided by N1 minus 1. So you just multiply the other side, give you this answer. Okay. So same for the second sample. Okay. And remember the independent, right? So remember the sum of chi-square is also chi-square, right? The sum of these two add up together will be a chi-square n1 plus n2 minus 2. So here come to minus 2. So that's why you have minus 2 here. Okay. Now finally, again, we know the independence, which also proved in that chapter. And now we are going to say why this is t. Okay. The numerator is this guy. Okay. This guy we have shown last step is standard normal. Okay. And this, right, we know this guy is a chi-square, right? So that's why z over the chi-square over the degree of freedom is t, right? That's the definition of t, right? And you can see this, this guy is what we have s of p squared. Okay. So that's why we have this expression give you a nice structure. Okay. So you can see that we use SP, right, to proxy for this sigma. Okay. So that's a little bit instead of S, but use S of P to do it. And the question? Any question? If there's no question, we go to the last test we're going to talk about today. It's called unequal variance. Okay. Is there any question? So if no, then we go to unequal variance. Okay. So it is very rare that you have equal variance unless you have a strong reason to believe they're the same variance. Maybe historical reason to believe so, or you are thinking about, say, you can have a judgment that is saying maybe you could think about the variance of people live in Hong Kong Island and Kowloon may not have different, may have different mean, but may not have different variance. You have some strong reason to do it. Otherwise, we always use the unequal one, right? Okay, that would be the norm. Usually unequal. Equal is only very rare event, but or you have some strong reason to do it. Okay, all the same. Okay, and we will not prove it. This is very complicated. Okay, but the formula is much easier. Okay, because we don't have the this, right? If we actually happen to know this, right? If you have x1 bar, actually is normal with mu sigma 1 square, right, over n1, right? And this will be n mu1, right? So then the case of mu1 minus, sorry, x1 minus x2, okay, minus mu1 by mu2, so this is 2, okay? And you should over this guy, right? Sigma 1 square over n, right? Sigma 2 square over n, okay? So this is a very standard way, right? Because x1 minus x2, right? Have a normal distribution with mu1 minus mu2, right? Sigma 1 square over n, 1, sigma 2 square over n2 because they're independent. So this will give you this one. Okay. So this is something that we will know. Okay. But now we don't know this, we replace by a sample component. Okay. So that is replaced by this, right? Replace it. Okay. But when we replace it, we have to use t, right? And here comes the difficult part, right? And what should be this degree of freedom, which is something very difficult problem. Okay, very difficult problem. Okay. So we will not explain why this is the case, except give you some hints. And we will give you the formula for this degree of freedom, which is so complicated. Okay, let's see. And when I say very complicated, it's indeed very complicated. Okay, what is degree of freedom? The degree of freedom is this humongous object. Okay, don't ask me why this is true. This is, yeah, someone say OMG. Okay, yes, OMG. But do you know that we don't really need to do it because calculator will give you the answer, right? And you can see with sample variance over this and all the thing, right? Very complicated object. Is this c square? Why this is the case? I don't know. We just give you the hint, but this is a object, and then we have this is called the floor function, right? The floor function is basically just run down. Okay. What actually means is if there's 3.2, we'll give you 3. 3.9 also give you 3. Okay. Round down to the largest integer. So just take out the decimal stuff. Okay. Just basically truncating the decimal number. Okay. To give integer, because we know how to do integer for the t, right? And I guess that should not come surprise to you, right? This is how we do the interval estimate, right? Should not be surprising to you. We'll explain, give you some reason at the end, but let's do the example, right? Here we have sample size 50, x1 is 40 and s1 is 4, right? n2 is 40. Almost the same thing, but except we have do not share the same population variance, okay? Then the calculation is easier for the denominator, but checking of the degree of freedom will be much more difficult. Again, the same idea here goes on. We have x1 minus x2, okay? Under the null hypothesis, this will be 0, right? And the variance will be, again, right, if we happen to know it, right? But we never know it, right? Okay. Then if you use t, right? Okay. This will be, we're estimating by this. Okay. And this is 42 and 40, right? So again, this is -2 here. Okay. This is coming from actual x1 minus actual x2. Okay. And let's see what this number is, right? And apply the formula here, right? You have S1 is 4, some here. S2 is 3, so 3 squared. And this N1, N2, N1, N2, okay? Give you -2.7, okay? And this is T of degree of freedom what, okay? So you have to check what degree of freedom require us to do a super complicated calculation, okay? Remember it's 2.709, okay? Go to the next page. Okay, let's do the super complicated calculation, okay? You may try to check and tell me whether I did it correctly. If I'm doing right, it should be 87.5 63, and you run down, take out the remaining number, give you 87. Okay, and the two ways to do it, right? Either you do the first way, or I do the second method, right? So remember the answer is 2.709 here, right? So all those negative, right? It should be 0, negative 2.709. You want to look at this one, right? So T87. Do remind you that actually, oh, I'm sorry. Is it, I'm going too fast? So let me slow a little bit. So the degree of freedom is 87. Which part I go too fast? Is up to this part okay? Hou Yi. Hello? Do I need to go back again? No, that doesn't matter. We have time, so let's try to hold back a little bit. Okay, so let me explain again what's going on here. So we have two samples here, the two population, 1 and 2. We want to try to check is mu1 is equal to mu2. Okay, and we get a data from here. We have x bar 1, x bar 2. We get some sample here, right? The sample will give us the sample mean x1, sample mean x2. We have the sample variance S1, sample variance S2. Okay, and we know that the difference of this, okay, we have a normal distribution with mean mu1 minus mu2, okay, and the variance will be sigma square 1 over n1, sigma square 1, sorry, sigma square 2, n2, okay. Suppose we also know sigma 1 square sigma square 2, okay. Since we don't know this, okay, it will be something like this turn out, right? Sigma this, okay, approximately T distribution with degree of freedom, there's something to be determined, okay? Actually, that turned out to be 87, okay? And we will have, or maybe we just do the, easier way, right? And right, so we are going to see this minus this, okay, minus what you have said, okay, over, so according to this, right, will be sigma 1 square over n1 plus sigma square 2 over n2 will be normal CO1, okay? But instead of this, what you're doing is, because you don't know sigma 1 and sigma 2, you replace, okay? We have mu1 over minus mu2, okay? You replace by S1 square n1 plus S2 square over n2. We'll have a T distribution with some degree of freedom, which to be calculated, this will be very complicated object, which turn out to be 87. But actually in this case, they don't have equal variance. Example name, oh, it's not equal. Oh, unequal, sorry. It's unequal, yeah, sorry, yeah. Unequal variance, so that will be 87. When they have equal variance, actually knows 88. Okay, that's not too much, actually that's not too much difference, but we just to be precise here, 87, okay? So you would be doing the same thing, okay? So that is how we end up in here. So now what we have is just, sorry, a little bit overrun, but just we're done. Okay, so this x1 bar minus x2 bar, okay, and this is 0, and we have negative 2.709. Okay, sorry, we should be talking about the t, right? T here, okay, and 87 coming here. We want to figure out this area, okay, and how to do that, right? Will be this area is given by t, this, right? Negative 2.709, degree of freedom 87, true, okay, and this gives you this area is two-sided, multiplied by 2, okay, so give you this answer. Way less than this, so you reject, okay, or you look at the 2.5%, this critical value, right? The critical value will be somewhere here, right? It's 1.8, 1.9, so this is 2.5%, okay? So you also reject, okay? So at the end of the day, you also do the same thing here. This is a trick. This is here, okay? And this is the denominator over there. Okay, and just bear with me 1 minute. I'm going to explain why the V. I mean, I'm not explaining, I just give you the hint. So turn out that someone, okay, prove this guy is following T distribution with this funny shape. Okay, this is actually what we have seen here, but only if we know all this thing. Okay, so that's why in practice you replace this. Okay, to get some idea. But other than that, we don't have a good explanation why this is a good one, but this is what it is. Okay, so far we end here. So I stay around to answer questions. I guess there's some, maybe there's some question here, but I should say thank you and goodbye. Remember tomorrow, Excel function, no, that is just input there, no particular function. So remember tomorrow, do of the homework too. Homework 3 has been uploaded, so you can do it, and also to do peer review with the same deadline, 13th of November. So I say around answer question. Bye. Thank you. If any question, let me know.
Hello, Mr. Cole.
Yes.
May I know that how is the grade? What is the grading system of this course? Is line curve or absolute grading?
I guess this is I think same for other classes because we abandoned the curving already.
Okay, but if you use absolute grading, so what is the cutoff score for A?
No, it's just based on the objective, right? I think you have seen the syllabus.
Oh, okay.
So
So
same for other class. It's not particular. It's not particular for this class. I mean, I think every class about the same procedure.
okay.
There's no particular different from this one. It depends on how well you achieved the objective, right? That is, it's not particular number for that.
Okay. Thank you.
Yeah.
I think I understand.
Yeah, it's no particular for this class. Same for every other class. Okay, any more question?